We're really excited to host this Mentee Showcase for 2023. And we're excited for you to hear more about the projects that we run in our mentorship program. Our mentorship program has been going for about 4 years now, and it's been awesome to watch it grow. We started with just 1 or 2 mentorship projects. Now we're running on average about 4+ mentorships a quarter. We run spring, summer, and fall for our mentorship program. And right now, as you can see, the fall session is open. So we did just open for applications. There are 4 mentorships that are added on there. If you have any questions about the program, so essentially you just click on this. Oh, it's not gonna let me change. Let me change. Computer's too smart for me. Careers, here we go. So when you click on that button, it takes you to our jobs board. If you didn't know about this, this is a great thing for you to know on our website. This is where our members list their open career opportunities. So you can see the 4 mentorships listed here. Once you click on them, then you can apply through the LFX platform. You'll have until August 12th to apply for those. If you have any questions, you can go to our Slack channel. And the group is called, I believe it's just RISC-V Mentorship Questions. So you can find that in our Slack channel. And that's a great way to ask questions. The mentors are in there as well as myself. And it's fun. People sort of answer questions for you because they know the answers. Each one of the mentorships does have a coding challenge just to prove that you have the basic level knowledge. I am really excited to announce that 2 of the mentorships that we are running are for undergraduate students. So you don't need a huge amount of experience. The goal of these is to give you experience and something to put on your resume and a GitHub link to share with individuals that you're looking to work with so they can really see what it is that you can do. I'm excited to also say that a lot of our mentees now have full-time jobs. And so I'm working with them right now to find out if they feel like the mentorship program specifically had any positive benefits in them obtaining these jobs. So it is really cool to see their progress over the years. And so I'm really excited to present you with the mentorships, 3 of the mentorships that we did in 2023. I'll just pause briefly. If anyone has any questions, feel free to throw them in the chat while I bring up the recording of our mentees. This is a paid program, by the way. We do pay the first mentee. We have so many applications that we have opened it up to, if the mentor can take them on, to additional individuals are able to participate in the mentorship, but it is unpaid. So that's just something to take into consideration because I think these are fantastic to have on your resume and great learning experiences. All right, doesn't look like there are any questions. If someone can just give me a thumbs up in the chat to let me know that you can hear it when it starts.
Hi, everyone. Today we're going to be presenting our project, addition of an open floating point on Open RISC-V core. This was done thanks to the collaboration of the LFX Mentorship Program and the RISC-V organization. And the project consisted on connecting an open source floating unit, in this case HardFloat, to an open source RISC-V core SoC, in this case Nucleus RB. My name is Aldo Balsamo. I'm a soon-to-graduate computer science student with interest in RISC-V and hardware design, currently working at Taiwan's top research facility, Academia Sinica, on innovative instruction sets to support post-quantum encryption schemes on RISC-V.
And I'm Shinasan Beg. I am an undergraduate majoring in computer science with a keen interest in hardware design and low-level programming, including compilers. So for the project, the main point was the whole project was around the RISC-V core, nucleus RV. So for a little introduction for that, it is a RISC-V core written in Chisel. Chisel as in constructing hardware in Scala embedded language. Uh, some characteristics of nucleus RV. It is a 32-bit variant core. It supports the I, M, and C extensions of the RISC-V spec. It is an in-order 5-stage pipeline core and fully parameterized. It is also used as the base RISC-V core of the SoC now SOC generator. So a little bit about the RISC-V F extension. Uh, it is one of the many RISC-V extensions, and the F extension adds the support for floating point compute in the RISC-V ISA. Some of the characteristics for it are that it is IEEE 754 2008 compliant. In contrast to the integer general purpose registers, it comprises of 32 general purpose floating point registers. It deals in single precision floating point numbers, meaning that it represents floating point numbers in 32 bits. Also, it includes instructions for floating point arithmetic, comparison, and conversions. So in order to add support for the F extension in nucleus RV, we took the support of hard float, Berkeley hard float. Uh, Berkeley hard float is a chisel module library for floating point operations. The interesting thing about hard float is that it uses its own recorded format for representing floating point numbers, in contrast to the IEEE format. It is because it was an attempt to handle subnormal numbers more efficiently in a microarchitecture implementation. Uh, the recorded format is actually abstracted away in the chisel modules, meaning that all the computation in the recorded format was held inside the chisel modules of the in the hard float library, while using the same interfaces that you would use normally in an FPU implementation, meaning on the upper level, on the abstracted level, we would be still be using the IEEE form. We will still be assuming the IEEE format. It includes the operations for floating point arithmetic and conversions to and from the IEEE 754 format to the recorded format. Here are some snippets for the parameterization done in the nucleus RV. In the on the left, we applied the F extension parameterization in the ALU, and on the right, there is the nucleus RV parameterization configurations.
So I'm going to discuss certain things that Hardfloat itself does not provide, and one of them are the CSRs, or the native floating point registers, ergo they're implemented by yourself. So for example, the F extension for RISC-V introduces 32 floating point registers, each being 32 bits wide, and also a floating point control status register called FCSR. The standard also introduces a set of new pseudo instructions built on the pre-existing instructions for accessing CSRs. Pretty much these are abstract pseudo operations that the compiler will take care of. However, they're really useful when you're verifying your code to know that the new CSR and its registers are working properly. So here is the FCSR itself. So it's divided by three parts, mainly these two over here, rounding mode called FRM, and accrued exceptions, our F flags. Let's go first with reserved. Actually, this is not really used currently, and it's mostly padding to get to the 32 bits needed for, keep compliance and standardization throughout the extension. But the important parts, as I said before, like rounding mode, that in here we have a table presenting them all. So the F extension supports both static rounding mode and dynamic rounding mode. The second one mostly to support things like C99 to require that still. and pretty much we'll like assign a certain rounding mode, which can be like towards 0 down to infinity and so on, or even just explicitly telling to our computer, to our FCSR, I need a dynamic one. Another one that we have are the accrued exceptions, and in this case, it's just to know if something happened during execution, we can save them somewhere in the CPU. So we have, if there was an overflow, underflow divided by 0, which can tend to happen decently often with um, floating operations. In these regards, we also had to take care in verification. So hard float comes with no guarantees that it's free or that it's free of bugs, or errors. And even though it has been used in other projects, we had to verify it properly. And this was really important because we cannot just assume that when we install, hard float into our system, it's going to work properly. So we verified all the arithmetic instruction thoroughly by generating extensive test benches using Python to give us shell code. So this will be a good example. So we'll have these test benches in which we'll put each one of the modules that do operations from Hardfloat, which, by the way, they're really well organized and they're very modular. So that overall even helped us to have a very good workflows when verifying the design. But regardless, we will generate our test benches with Python, invoke inside of that operation the module that we need, and then we'll execute it. We will do this by, on Python, generating these mathematical operations, verifying them using this programming language. And once we have them, we will feed them back to our design and check if the results are the same as the results that we had from, let's say, Python in our case. So we will, for example, say our test cases on a sequence, which is pretty much just imagine a vector of vectors, and we will have input A and B, and using Python, we will pre-calculate what's the right answer. Then we'll put these two values A and B into our, let's say, F addition / subtraction, and compare the outcomes to whatever Python is giving us. And this is what we did for every single operation inside of Hardfloat. Actually, all of them were compliant with what we were expecting and they worked properly, but we still needed to do this to verify that it was going to work properly at the end when we integrated fully into our core.
So an important part of adding a whole new extension is to ensure backward compliance compatibility. So first it was tested to see if the new parameterization would not affect the compliance of already implemented extensions. As such, we tested the possible selections of combinations of the extensions. For example, first we switched the M and C extensions on while keeping the F extension off. So, and then running the compliance for C and the C instructions, and then for the instructions and the I instructions, then turning off the M in the parameterization module, and turning on the F extension, F parameterization module, so that we could so that both C and F extensions are up and running while the M is off, and then test the C instructions again and the M instructions again, and this time with the addition of F instructions, and so that we had to combinatorially check for all of the combinations of the extensions. So for integrating Hardfloat to Nucleus RV, we had to introduce 3 new modules for the floating point instructions. For the first one was floating point decoder, then the floating point register file, and the floating point control unit. These were in addition to the ALU. So for the decoded bits, we used the FMT and Funct5 for wires from the FP decoder in the FP control unit to control the floating point data path, which included controlling the floating point operations in the ALU, detecting data hazard of floating point load instruction, and structural hazards. Since there are no branch instructions in the floating point, we did not have to cater the control hazards. We we also have to control the selections of floating point register values instead of the integer register values in the respective instructions. We also had to differentiate the forwarding of RS1 and RS2 integer data during the data hazard pipeline from the floating point data in the branch unit and jump unit. We also had to handle the selection of FCSR register for dynamic rounding mode. So in this diagram, there's in the decode stage, the above modules are the same, which we did not have to change. The only additions were the floating point, FP decoder, FP control unit, FP register file. We just had to cater some of the wires from the existing implementation. And then in the execute stage, uh, we had to integrate the floating point ALU inside the integer ALU. So one of the characteristics of hard float is that all but the division and square root operations were combinatorial operations and hence uh, required a single clock cycle. The both the division and square root operations take arbitrary number of clock cycles to complete, and so we had to stall. We had to signal the program counter to stall until the completion of these operations. So we combined our ALU with many of the operations found in the FPU while maintaining almost identical data paths.
So our experience in summary. So first, we would like to give some of our key points, and those were like open source IPs are vital for the advancement of open source chip development. And this is a clear example of it, in which we had like a RISC-V core, and we opened one, and we were able to really give it like a really important milestone to it by connecting it to a floating point unit by just accessing to free IPs that we can get online and just adapt it to our needs. Another thing was Chisel was a great tool for fast development hardware design. I didn't have any experience with Chisel before doing this. However, in a matter of 2 weeks, thanks to our really good mentors, I managed to learn and became really proficient in it to a point I was able to contribute to this project. And many thanks to our mentors for guiding us throughout all this project, having patience with us. I would like to now we will both say our like best and maybe hardest or most difficult experience on the project was I think the worst one to say so was actually that it was very challenging to go into like a very large project like this one and having to tackle it by almost sometimes breaking it completely to understand how it works. But simultaneously, actually, the best part I think it was exactly that we got the opportunity to work on a very large project with really good guidance and like mentorship throughout it that made this less scary almost.
And the most hardest part of the mentorship was that uh, the conversion from the IEEE format to the recorded format. I had to make my own modules in the bit manipulations and whatnot, and integrate my own algorithms in that, and that took a great deal amount of time. And the most exciting and the fun part for me was coincidentally the exact same thing, because I then had the chance to get into the math and geek out on the implementation and to try new approaches on how to do that. And that is one of the uh, main advantages or exciting part about RISC-V is that it's open and uh, we can implement our own ideas and our own the and our own developments into the ISA and implementations, while also working with like-minded people, just like Aldo and my mentor Shazib and Talha. And it was a very good experience for me.
Thank you very much for having us today.
So hi everyone, I am Dev and today I'll be discussing with you all the project that we did at Spring 2023 RISC-V Mentorship titled Integrating Tiling Uncached Heavyweight Version in the Existing Caravan Framework. This was a group project done jointly by me, Dev, along with my friend and colleague Mohsin Siddiqui, who is a software developer at Softcom, under the esteemed guidance of our mentor, Mr. Shehzeb Kashif, who is a RISC-V design engineer at Intensivate and a research assistant at MERD. As I said, we worked on integrating the support for tiling uncached heavyweight in the existing Caravan. What is this Caravan? Caravan aims to help all chisel developers by providing them pre-made buses. They can use Caravan to generate a bus implementation of their desire with the desired characteristics by changing the config file of Caravan. Currently, Caravan supports uh, Wishbone, Tiling Uncached Lightweight, and we worked on implementing Tiling Uncached Heavyweight version in the existing framework. Actually, there have been several implementations of chisel-based bus protocols, but they are either obsolete or have been used in very complex designs, which makes them not reusable. Reusing them gets very tough and requires a lot of efforts. These efforts are being reduced by Caravan by providing the chisel-based designers a unified framework wherein they can generate the bus implementation of their choice and integrate in their IPs, be it FPGA based or ASIC based. Let us understand this interfacing of Caravan within the network that we have between the master and several slaves. Suppose we have a master, a RISC-V core here as an example, connected to several slaves, be it an SPI, UART, or memory. Caravan resolves the problem. Caravan interfaces all the peripherals through a single set of generic IOs coming from the master. There are no specific IOs required for specific peripherals. We have a single Caravan framework in the center that is being connected on one side to the master and other on the to the peripherals, and in between lies the bus implementation. In the next slide, we can see how we can use Caravan. So this particular diagram shows how Caravan has an adapter architecture. We have a host adapter and a device adapter. In this diagram, we have an example of tiling uncached lightweight version host adapter and a tiling uncached lightweight device adapter. Host adapter on the left has generic request and response IOs to and from the master. The device adapter on the right has request and response IOs connected to the slave. And in between the host and the device lies the bus implementation of your choice. Here, tiling uncached lightweight version has been chosen, so we have the required set of pins for the tiling uncached lightweight version in between. Understanding tiling uncached heavyweight version. So as I said, there was a support for tiling uncached lightweight version already in the Caravan framework, and our task was to add the support for tiling uncached heavyweight. So Tilink is a bus protocol that is an open source bus protocol given by Sci5. It has several versions: the lightweight version, heavyweight, uncached weight, uncached heavyweight, and uncached lightweight. There's also a cached version. So, but our task was to add support for uncached heavyweight version. The lightweight version has a support for get and put operations, which are more or less like a read operation and a write operation from and to the memory. Heavyweight version has a support for atomic operations, hint operations, and a support for burst. What are atomic operations and hint will be discussed in the couple of next slides, and burst will also be discussed there. Yeah. So atomic operations are nothing but arithmetic or logical operation between two operands. One operand is sent by the master and other operand lies in the memory or the slave itself. These two operands are modified. The operation is being performed based upon the user's opcode or the master's opcode, and the updated data is written back to the memory. There are two subclasses, as I said, in atomic operations: arithmetic and logical. Arithmetic again has subclasses of minimum, maximum, minimum unsigned, maximum unsigned, and addition. Logical has subclasses of XOR, OR, and swap. The decision for arithmetic and logical operation is taken by the opcode signal, and decision for the subclasses of these operations is taken by the param signal. Hint operations are special category of operation that gives a hint to the slave that what is going to be the next operation, next opcode, which the slave must expect from the master. The response to this hint or the intent message is hint acknowledgement response from the slave. As mentioned here, intent message indicates the requester's future intention for a data block. What can be the possible operation that the master would want the slave to do in the upcoming cycles? So yeah, this was a 3 months project wherein we worked on integrating the support for tiling uncached heavyweight, support for atomic, hint, and burst operations. There were several integration challenges throughout this 3 months journey. There were several ups and downs. Let us discuss them one by one. First one is, how should we map our opcodes and params? As I mentioned previously, that we need to map the type of operation through this signal A opcode and what type of this operation through A param. For instance, it's an addition operation that would be decided by param, and it's an arithmetic operation that would be decided by the A opcode signal. Previously, we had only two categories of operations, which was get and put. The decision of A opcode was taken by a single generic pin is right, which was available on the left of the host adapter. This is the host adapter. The host is sending requests to the slave. Suppose is write is active. This means the put operation has to be performed. A data has to be written to the slave. But now we have several other candidates in the line. How should we map these candidate opcodes through the A opcode signal? We don't have sufficient generic pins to make that decision. Similarly, we don't have sufficient pins to decide what type of arithmetic or what type of logical operation it is. Again, we are in a problem. Here, two question marks indicates the problem. To solve this, we leverage the conditional synthesis provided by Chisel. We add conditional pins on the generic interface that helps us to decide the type of operation. Again, I mark the word conditional. These pins get synthesized in our design only when the adapter has been configured to work for the tiling uncached heavyweight version. These pins is arithmetic, is logical, is intent, param, and size are indicative of their use case. Is arithmetic is going to tell us whether the operation is an arithmetic operation, logical for logical, intent for a hint operation. Param helps us to decide what type of arithmetic or logical operation it is, and size helps us to make the decision on whether it is a burst operation, and if it is a burst, what is the total number of beats that we should expect. So we added the support for these conditional pins in our design. And we must not forget, as mentioned here, that these pins are active only in case of TLUH host adapter and not any other existing bus implementation adapter in Caravan. The second problem that we faced was with the atomic operations. Atomic operations might sound simple. We are just performing an atomic arithmetic or a logical operation, but it's not that easy. It's a three-step process wherein first we read the existing data from the memory, we perform the operation, the modify state, and then we write back the updated value back to the memory. Performing this in a single cycle is not possible. Hence, we had to add a support for a state machine that could do this the entire process in 3 cycles. First state is the idle state, second is the UH state, and third is the wait for response state. Idle state, we send an address to the memory to perform read operation, we fetch a value. In UH state, we perform the operation, whether it is the arithmetic or the logical operation. And in the third stage, we wait for the response of an acknowledgement from the memory. In response, the memory sends us the value which was previously written in the memory. So we get to see the old value as a response from the memory that indicates that the atomic operation has been successful. This state machine also was a conditional state machine. This will be active only when you have a support for tiling UH and not in any other situation. The third problem, and a very severe problem, was that during burst operations, when we have several beats of messages coming from the host, the control signals like opcode, parameter, and size should not change. Yes, they will not be changed by the host, but we cannot rely on the host to not to change these signals. We want to be secure and safe. To be secure and safe, we register the control signals like opcode, parameter, and size during the first beat of the burst when within within the registers that we have got on our adapter. We store the values of opcode, parameter, and size, and during the next beats of the burst, we send or we drive these signals through the registers and not through the values coming from the master. This brings us the reliability that even if there are some glitches in the signals, there will be no problem, there will be no intervention in the operation of the bus implementation in the Caravan framework, and any errors would be avoided in that situation. And yeah, so as mentioned here, we have added decrement counters. The counters were loaded during the first beat of the burst according to the data signal, the size signal coming from the generic interface, and these counters incremented on every beat, and when zero, that indicated end of the burst operation. Testing and verification part, we performed two kinds of tests. First was the regression test. In regression testing, we performed put operations, we performed atomic and hint operations, we performed get operations, wherein we tried almost every opcode and operand permutations and combinations, and we tested it for bursts as well. SBT test is a test that tests whether the existing frameworks have been disturbed or not by adding a new one. And fortunately, SBT tests were passed. So all the existing frameworks are okay with the presence of tiling uncached heavyweight version in the existing Caravan framework. So here I would conclude my talk and our project. We could have the implementation of atomic and hint operations, which enhances the functionality of the Caravan framework. We overcame integration challenges through testing and verification and constant debugging, observing those big waveforms and coming to conclusions. This opens possibilities for advanced features of Caravan, and of course, Caravan is open to all open source bus frameworks which can be integrated in the design. Thank you so much. I've added two links. Caravan, here is the link to the documentation of Caravan, which will help you to set up and will help you how to use it. And this is the mentorship blog that we had written. This has very minute details of every step that we took. It has detailed explanation of tiling uncached heavyweight, what were the integration challenges. I have discussed them superficially, but they are available in much detail in this blog. If you have any doubts, you can reach out to us, any three of us. We are always happy to help you all. Thank you so much.
Hello, everyone. My name is Caravan, and I'll be presenting this talk about my mentorship experience at RISC-V as a RISC-V education apprentice under the title of my talk, Overcoming the Learning Curve. First of all, a little bit about myself. I just recently graduated from computer engineering at the University of Ottawa, and I'm especially interested in digital hardware design, FPGA development, embedded systems, and I'm currently working at an engineering position in the field. I'm also highly interested in aviation and photography. The position's title for my mentorship was RISC-V Education Apprenticeship, and this was the description of my mentorship. In my eyes, some of the important key statements of this posting was to make a difference and open standard project, contributing to an open standard project, because these greatly summarize my perception of the tasks of this mentorship and, of course, this talk. The objective of this position was to further activate the potential of RISC-V by making a learning pathway more accessible, especially more accessible to those who are or who might be interested in what RISC-V already offers by nature. We know this fact by one of the main features of the RISC-V ISA. The concept of open architecture or having a technical background is enough for an individual to broaden their horizons in developing their own hardware solutions with much less vulnerability against the minefield of highly licensed proprietary solutions. This is where making a difference becomes important. In the age of digital transformation that we are in right now, it is clear that with every new generation of candidate engineers and enthusiasts of the silicon development world, we potentially have more and more individuals every day, every year, seeking to make an impact, make a difference, to contribute to what we already achieved. And this has already been, to some extent, made possible with RISC-V and its open nature. What makes open source alive and fruitful is the community that keeps it so. But this advantage can only be achieved with proper organization of resources. RISC-V, with its open nature, has a great deal of resources from within its community with many projects, like processor design projects, RISC-V emulator projects, individual FPGA projects that involve RISC-V, CPU cores, etc., and even more commercial solutions that adopt RISC-V. Especially in the past few years, RISC-V is growing, as you might already know, being widely adopted in the industry with its benefits like modularity and simplicity being more recognized for its potential in areas like vector processing, secure embedded applications, graphics, and AI, and much more. So when we look at the growth that is taking place in the RISC-V ecosystem, we can summarize this expansion by a couple of factors, which can be summarized into these. First of all, we can count community-driven development. RISC-V ecosystem is enriched by numerous individual projects and implementations, like we just saw in the previous slide, simulators, CPU implementations, many such projects, and much more. Another factor is industry-level expansion. RISC-V is rapidly gaining ground. The formation of the RISC-V Alliance and strategic partnerships that are taking place right now with the semiconductor companies and organizations are a testament to this. But aside from these two factors, there's one more thing, and I think that's the most important one. In order to keep such an ecosystem growing with contributors and partners, resource accessibility and motivation must be boosted at the beginner level. The only problem is, from what I personally see at the beginner level which mostly consists of students and novices who are interested to get into this field but are slightly overwhelmed. The beginner level is not a context that encourages or reflects the potential of RISC-V at a desirable level to its potential contributors, to the novice developers. By this I mean that even though the RISC architecture is taught at the educational level, it is still not as impactful as it has the potential to be. To mitigate this gap, it made sense to create a base level learner's path for those who are new to the world of RISC-V and can be overwhelmed with its potential. This is why during my mentorship, we planted the seed and created the RISC-V Learn repository. RISC-V Learn is a community-driven compilation of RISC-V resources and learning material. The list is dynamically updated by the community and categorized based on different contexts of the RISC-V scope, taking into account different levels of experience and knowledge, allowing anyone who is interested in RISC-V to discover the RISC-V resources and relevant content in the form of courses, software, documentation, articles, videos, and much more in an organized fashion. Since RISC-V is a dynamic ecosystem by itself, it is vital that this repository also stays so. It is the community's duty, in a way, to contribute to this repository, if they can, at some point, with their knowledge and resources. I certainly will do so. Thanks to the RISC-V community and my mentors, Megan and Raphael, this resource hub already has the community's attention and is constantly receiving new contributions, as you can see on its GitHub page. I highly encourage you to check it out. It has clear instructions on how to contribute and how to use it, and it has an initially well-categorized set of resources that can be helpful for anyone who's at the beginning stages of their RISC-V journey and want to learn more. While we took the first step towards this gap in the RISC-V learner's path, the RISC-V Education Apprentice position, the RISC-V Education Apprentice Mentorship, is still an ongoing one, and it's still ongoing. There's many to be accomplished in this project. I encourage anyone who would like to dive into this aspect of RISC-V, who feels confident in documenting and organizing, to apply to this mentorship, as it can prove to be a useful path in your career, while also allowing you to impact others' learning experience in RISC-V and amplify the potential of RISC-V. As I said, there's still a lot to be accomplished in this project. In my opinion, some of the further developments could be to extend the range of contents with even more organizational categorization, to make the roadmap more definitive, covering more paths depending on different sub-focuses, FPGAs, RISC-V development board guides, projects, ongoing technical projects that are open to contribution in the RISC-V world, and much more. This platform can even be morphed or integrated into a centrally maintained but community-driven learning hub, like a wiki. There are many well-structured examples of this out there already, such as the one for C++ or ArchWiki. These tasks are not hard to achieve, given the power of community that RISC-V thrives on. Aside from my RISC-V mentorship, I'd also like to talk a little bit about overcoming the learning curve, which is also the title of my presentation. In contrast to the fact of how massive an industry the semiconductor industry is, it is still a niche and unique area of focus for those of us who are up-and-coming developers and want to invest in this field, invest their time in this field. Even for students who are studying and specializing in the computer, electronics, and software principles, the thought of pursuing interest towards digital logic and computer architecture is generally an overwhelming one, compared to those that involve less hardware, at least. There are much more organized and open access resources, and more importantly, much more encouragement for those other disciplines and other pathways that one can specialize in the tech world. But we all know that the more we dive into this ocean, the more obvious it turns out to be worth it. The two dominating perceptions of overwhelming learning curve and versus a path that is worth investing my time in certainly go head to head against each other at the early stages of one's learning path. It always was apparent in my path, at least. So I want to share a few insights and habits I found helpful through my process to challenge the learning curve. First of all, constant exposure to the semiconductor ecosystem is necessary, because one aspect of how it feels like a goal too far away to achieve during school, or a really scary, is because the industry and the research mediums might be looking too scary or too advanced to get into for ones who are at the early stages of their learning process. As a solution to this, finding a couple newsletters, RSS feeds, YouTube channels, articles, and such resources to follow the up-to-date developments and to constantly expose yourself to, definitely, in my opinion, accumulates into a source of confidence. So it shouldn't be underestimated. Exposure is key. When you start seeing some of that information in this process repeat in your eyes, when you see more and more of the same information, connecting the dots automatically and slowly start happening in your mind, in my opinion. And this adds to that confidence. And not only confidence, it'll also give you insight, and more importantly, the thrill of discovery will motivate you to keep engaged and push yourself to learn more. This was the first one. Secondly, and more importantly, it could also be very motivating and progress inducing to explore the wonders of open source and community resources and tools. Because another factor contributing to the overwhelming nature of this field is that learning resources and examples are not nearly half as accessible as what we see in software-related practices like web development or data science in the hardware side of things. Both resources and the tools for diving into this field are less accessible and needs more democratization. But this gap actually is very well remedied by the huge open source community RISC-V has. RISC-V is a great example of this. Exploring open resources is your best bet for acquiring the initial knowledge. And it is great because it also shows you how to utilize open tool chains and examples like simulators, FPGA implementations, synthesis tools, RTL to tape out EDA tools, and much more. So you can put your knowledge into more than that by implementing it. This is the best form of exposure. It'll build up your confidence towards learning more. If you are at the initial stages of your learning path, I encourage you to explore RISC-V Learn repository because it provides exactly what you might need in this sense. If you are already ahead of these steep parts of the learning curve, you probably already have made use of useful resources in your path that brought you to this level of experience. Then I encourage you to consider contributing to the RISC-V Learn repository with such potential resources. This way, the full potential of RISC-V can be unleashed. Thank you very much.
Awesome. It's so fun to watch from the beginning to the end and just how much everyone learned in the process. So I'm really proud of all of our mentees. It's been an awesome experience to work with them, and I'm really excited to see what happens next. So again, I do want to reiterate that mentorships are open for application right now. If you are interested in applying, please go to our careers page, and that's where you can see all the details. Let me grab you these links again so that you can review those. And one more thing I want to say, especially to our mentees and our mentors who have participated in these, we do offer travel scholarships to attend our events. I feel like this is something that people are not aware of. I'm putting those links. There you go for the mentorship program and our careers page where you can find. So the mentorship program link tells you more about the mentorship program. The careers page shows you what 4 mentorships are open right now for application through August 12th. Now, the last thing I want to tell you about is our scholarship program to attend our events. This is a full scholarship. It includes travel wherever you are in the world, hotel room, transportation to and from the airport, and your ticket to attend RISC-V Summit North America. What's really exciting about this year is we're also hosting a hackathon and a career day. So the hackathon will happen on Monday, and on Wednesday, individuals will be invited to present their hackathon solutions. This is an awesome way to showcase how your brain works. If you haven't seen it, I'll grab a link for that as well, but I highly recommend you watch the hackathon that we just did in the North America Summit. You can watch the presentations and see the details here. The hackathon was really fun, and it just blew our expectations. People were so excited about it. They had such a good time that we decided to bring it to North America. So in North America, we're going to do those presentations, and then we're also going to be working with member organizations who are hiring to meet with individual students and job seekers. So if you feel like you are actively contributing to RISC-V, if you feel like you are a participant that I could ask someone in a working group, do you know this person? And they could say, yes, these are the kind of people we're looking for. People that are actively participating in RISC-V, making it better. I'll give you an example. A person I met in Barcelona this year, attended last year, met someone at the conference, and now works for them. I mean, these mentorships, these travel scholarships to attend our events. These are the kinds of things that can really launch your career. So I hope you will consider reviewing those applications, apply for mentorships, become active in the community, review the GitHub repo that Kamal and other mentees have worked on. Like I said, we are considering running that mentorship again. So if you are interested in that, feel free to reach out to me on Slack and just let me know that you're interested. And then if people are interested, we will run it again probably next year in spring. But other than that, any last questions before I sign you all off? Give me a minute to think about it. It's just so fun to host these. So I'm really grateful that you all showed up. Again, this recording will be available in the exact same place that you registered for the event and entered the event from today. And it will live on there, and we will continue building our programs. All right, looks like there's no questions. Thanks everybody so much. Have a great day, evening, night, and we'll look forward to seeing you again soon. Bye.